No, David.
Okay, so let me get started with the Friday seminar today. So thank you very much for this opportunity to share my recent work in collaboration with Tony sitting there. Today I'm going to talk about extra-dimensional axion in 5D Warped Orbifold GUTs. This will be based on this just published paper and also another paper that hopefully appear in April. So here's outline of today's talk. I'm going to first talk about why we care about the extra-dimensional axion in the context of especially the axion quality problem. And then I'm going to tell you an interesting way to get the lower bound of axion decay constant if you try to embed the extra-dimensional axion scenario model into the 5D GUTs. Okay, where GUT is gauge unified theory. And then I move into the other trial to embed the extra-dimensional axion in the flight of warp, okay, for the purpose of relaxing the lower bound of the decay constant. Okay, I'm going to ask if we can get the relaxed lower bound of the axion decay constant. Maybe because the as far as you work on the phenomenology, you prefer to have the lower decay constant because that gives you the stronger strength of the axion coupling to matter fields, gauge sector. So it's better for experimental search. And also in this part, I'm going to get into slightly more details of the extra-dimensional axion quality. And then finally, I'll conclude this talk by giving a brief sketch about a strategy to suppress the all universe suppression of the axion. That is always a problem, okay, as far as you work on the extra-dimensional axion scenario. So why do you care about the extra-dimensional axion? Okay, so let's forget about the UV details of axion model, okay? But then in 4D, we just have an axion angle, okay? And as far as its potential is given by this, okay, and as far as its potential minimum lies in the original field space, axion is serving as a perfectly good solution to a strong speed problem, okay? Perfectly explaining the null observation of sector violation so far. Now let's suppose due to some non-UV region, you have a correction to potential, which is denoted here by orange. Okay, delta V. And let's say at the moment that is aligned with the axion potential induced by the QCD confinement effect, which is denoted here by the blue. But then green, which is showing the net potential, is still remain. It will still have the potential minimum at the original field space. Okay, in this case, however large correction you have for the potential of the axion, doesn't matter. Axion remains perfectly good solution to a strong speed problem. But now let's consider the other scenario where the correction, which is given by the blue, is now misaligned, is giving misaligned contribution to the potential, okay, due to QCD confinement effects. But then you will see here, you see that the net potential, denoted by the purple, has potential now, corresponding to some point in field space deviating from the original field space. Okay, in this case, it's on the model to have the shift of the global minimum. Okay, and as far as that shift of minimum, which is estimated by the ratio of delta V to V, as far as that's greater than 10 to the 10th power, okay, axion is meaningless. So you lose the motivation for introducing axion to the standard model.
Where does this correction come from?
Where does this correction come from? Okay. There can be several sources to this. There can be several sources to this delta V correction to potential. Okay. I'll give you a few examples here. Okay, but there can be much more. A full list of I don't know, like several lists of complicated mechanisms that gives you the correction to potential. Okay. For example, okay, if your axion theory has the gauge group, okay, which where you have a small symptom effects becomes important. And if you have the higher dimensional operator made up of 4 fermion, okay, and which is also gauge invariant. So if you have 4 fermion operators sitting in the Lagrangian, which is gauge invariant, and then you can use that 4 fermion operator to close fermions that are more immediate from the smallest. Okay, and because the coefficient of this higher dimensional operator is in general complex, the point is the potential contribution to the axion potential coming from this small index will give you the misaligned contribution. Or if you rely on the Petrkin model, because Petrkin symmetry is a global symmetry, if you follow the common law of quantum gravity, which tells you that there's no exact global symmetry, but then you may, Lagrangian, as you go to the UV, you may find this U1 Petrkin breaking operator sitting in the Lagrangian. But then, because in general this coefficient is complex in general, the correction to axion potential coming from the global symmetry breaking operator gives you another misaligned contribution to potential. So the point is, whenever you work on the force field theory of the axion model, there's always this subtle issue of the what is the eventual net potential of axion, okay? And whenever
slides, the instant contribution, you mean additional instant contribution to the axion's potential, or
small instant contribution.
outside QCD? Some
It-
arbitrary.
It can be QCD, it can be dark gauge group, but yeah, it can be any instant as far as the axion coupled to that gauge group.
But it can be within QCD.
Yeah, it can be also, this can also happen in the QCD. Okay. In the case, for example, where, I don't know, you have more charged colored fields in the UV. Okay. When you find the beta function of the QCD in the UV. Okay. And then, okay, in that case, if QCD loses asymptotic freedom as you move to the UV scale, in that case, in that kind of UV completion of QCD, and then the small instant effects can be important for QCD. Yeah. And if you have a 4-core Gongjun operator, then this can give you the misaligned contribution.
Yes, but let's say take a QCD example. Let's say I have a small instant in the will they misalign my QCD vacuum?
Yeah, I think so. So that can give you a line contribution misaligned, but you don't know because you don't know the base of this question here. Okay. So whenever you work on force field theoretic axiom model, you always have to deal with this issue of equality. Okay. So it's very messy to work in the force field theoretic axiom models. Okay. Even if these days, I don't know, like 70% of the young generation are working on the axiom physics. Okay. Okay. Then, given this problems that we have in axiom solution to Stokes problem, now you may ask, what if we have the other extra-dimensional, the other models for the axiom? What if axiom can appear without introducing the global U1 symmetry, and if we don't need to introduce complex scalar? But then, in this situation, we may avoid at least the second source of Pauli problem, okay, due to the symmetry, the breaking of the global symmetry. And if this and it turns out that this is possible. For example, in fiber theory, when we assume some particle U1 gauge symmetry, and if we can have the zero mode, especially of the fifth component of the Bird gauge field, and it turns out that the Wilson loop of that fiber gauge field around compact dimension can be identified with the angle, which can play a role of the QCD axiom. So this is what I'm going to refer to as the extra-dimensional axion, okay, from here on. Okay, so extra-dimensional axion is at least advantageous, I'm telling you, in the context of a quality problem, okay? So that motivates you to think about the extra-dimensional axion seriously now. And whenever you have extra-dimensional axion, the decay constant is not determined by the dynamics of the radial mode, but that will be determined by the gauge coupling of the higher dimensional gauge theory and the size of the volume of the extra dimension. This is kind of a universal feature that you can have whenever you have an extra-dimensional axion, independent of the detailed origin of the extra-dimensional axion. It doesn't have to be one form. It can be an arbitrary higher form, okay? But this feature is universal to independent of the kind of extra-dimensional axion. So that means if you have interesting constraints on these parameters, parameterizing the axion decay constant, you can get very interesting constraint on decay constant of axion, okay? Okay, but then in this talk, I'm aiming to talk about the constraint on extra-dimensional axion decay constant. Okay, and for that purpose, let me think about embedding extra-dimensional axion into the very well-motivated extension of standard model, which is the GUT model, where the gauge coupling unification happens at certain high energy scale. Okay. For example, in 4D, okay, if you think about the supersymmetric standard model, MSSM, and there you have nice unification already at the 1 level, okay, happening at the 10 to 16 GeV energy scale. And there, the 3 gauge groups gauge coupling unifies at the inverse of 24, where alpha is basically G squared divided by 4 pi. But now then the question is, if we now promote this MSSM gauge group in 4D to the 5D gauge theory, where the gauge fields propagate throughout the okay, at the moment, the flat compact extra dimension, then now we can ask, for the purpose of constraining the decay constant, we can ask, does 5D GUT constrain these parameters, parameterizing the axion decay constant? Okay, if so, and then we can get very interesting constraint on the extra-dimensional axion's decay constant, which will determine the strength of the decoupling of axion to matter fields and photon and gluons. So therefore, this is very important for the experimental search of extra-dimensional axion. Okay, to understand the running of to understand how gauge unification can happen in the case where MSSM gauge field, MSSM gauge group is promoted to the 5D gauge theory. Let me consider, for simplicity at the moment, the radiative correction to the photon self-energy. Okay. But then for the purpose, let me introduce some charged field under this U1 gauge group, U1 hypercharge, let's say. And to regularize the divergences that appears in this radiative correction, let me also introduce some regulator, a PV field. Okay. And if you work out the KK spectrum of these two fields, charged field, PV field, you will find this kind of spectrum. Okay. Where the blue shows you basically the KK spectrum of the charged field, and orange shows you the KK spectrum of the PV field regulator. And what this shows you immediately is for every single KK excitation of the charged field, there's corresponding KK excitation of the PV field regulator, whose mass is importantly comparable to, is always greater than the UV cutoff. So what does that mean? That means simply each KK excitation of a charged Berg field contributes to this photon self-energy by log of UV cutoff. So now let's say you have capital N number of the KK excitation for this charged field, okay? And let's take into account all those guys' contribution to the photon self-energy. But then by dividing the UV cutoff by the equal separation between the KK spectrum here, which is 1 over R, which is equal to the KK mass gap. In flat extra-dimensional scenario, you can get this weird expression as a photon self-energy, which just tells you that the gauge coupling running in flat extra dimension follows power law instead of logarithmic running. Okay, the surprising fact was, I don't know, was found more than 20 years ago by Tony and Keith Deans and Emilian Dudas. So, given this understanding for the running behavior of the gauge coupling of the 5D gauge theory, okay, propagating along the flat extra dimension. Now, if you want to have perturbative gauge unification in flat extra dimension, it can be possible only when you have the KK mass gap comparable to or greater than the GUT scale. On the other hand, the axion decay constant turns out to be given by this expression, meaning that decay constant is basically given by a border KK mass gap, or like 1 order of magnitude smaller than KK mass gap. So therefore, combining these two, if you want to have an extra-dimensional axion compatible with the gauge unification in 5D MSSM, that tells you decay constant, which is KK mass gap, should be greater than GUT scale. So this was the core essential arguments that the Katie Fraser was giving was telling us in her seminar here last year, okay, as a last speaker of the last semester seminar. But once you see this, if you work on the axion phenomenology, okay, seriously, in searching for the axion, you're not really satisfied with this very strong constraint of decay constant. That's because you know that the relative abundance will be saturated. So that's because you know that when decay constant is order 10 to 12 GeV, axion is already making contribution to cold dark matter. Axion can serve as like a dark matter, explaining full abundance of dark matter of current universe. Okay? And so given this, now this tells you there will be too much relative ones of axion dark matter if this is really true.
Are there ways to relax this constraint?
Yes, there's several ways to rescue the high decay constant axion dark matter scenario. There are many. Okay? You can think about entropy production to dilute the relative abundance, or you can have some exotic alignment mechanism. Okay, allowing your axion to start at some point. Okay, which is still far away from truth. Okay, but that's just model dependent state.
You just need more model building.
Yeah.
Yeah, but there's tuning in some of those too. There's tuning in some of those solutions, right? The initial.
You can also, yeah. You can also think about misaligned initial angle
You
belief.
have to tune it to be like very close
Yeah.
to zero.
This is one solution.
You
10 to the minus 2 of
Yeah.
pi, right? 10 to the minus 2 pi or 10 to the minus 3 pi.
yeah,
Are you gonna say why this is the corrections to the potential now? You're not gonna worry about them? But you started by saying that there are corrections which will offset the potential, and you lose the solution.
The motivation for, axion.
Yeah, and now you went to the 5D case, but how do I know there's not the same corrections?
Oh, so there can be several
Or-
sources. Yeah,
Different corrections.
several sources, but what I already told you is, as far as extra-dimensional axion scenario is concerned, you do not have the complex scalar, 4D complex scalar, whose phase is identified with axion. So you can avoid at least those dangerous higher dimensional operators, giving you the misaligned contribution to potential. So you can avoid at least the second source of the equality problem. But you have to check whether other sources can spoil the axion solution. I'm going to get to this point later. Okay. But extra-dimensional axion is at least can be argued to be more advantageous than the force field theoretic axion models, because that can avoid the higher dimensional operators. Dangerous PQ breaking higher dimensional operators.
So how are you avoiding the higher dimensional operator?
How what? Sorry?
How are you avoiding the higher dimensional operator?
Because I don't have a complex scalar. There's no global U1 symmetry. Okay, for having 4D.
What is the axion? Because you said we got a supersymmetric gut, so if it's a scalar, it's got to be complex.
Yeah.
So you have a complex.
Yeah. However, the radial mode does not determine the decay constant. That's the point. Therefore, in other words, you may worry about first, because you can still have in supersymmetric model, because this extra-dimensional axion will rise as will form the complex scalar components of some supermultiplet, okay, parallel supermultiplet. Indeed, you have still a complex scalar field there, and extra-dimensional axion will appear as a phase mode. However, because of gauge symmetry, you cannot have powers of this complex scalar in the Lagrangian bins because of gauge symmetry.
but let me just also.
Yeah.
It's because the axiom was embedded into a gauge field. I do that, that's
Yeah.
the main.
So you can have either low. So if you have
So axiom
Is the scalar component
is
of the
A5 or
A5.
A5, yeah, that's
Mhm.
one. So it has extra protection.
Okay.
in that way, you can avoid at least some powers of this complex scalar. Okay, and this complex scalar component of some chiral multiplet will appear as a log of that field plus the complex conjugate of that field in the Lagrangian.
So things like, I don't know, FB quantity square. higher dimension.
Yeah.
Maybe that doesn't.
Yeah. So Kit, I will get to that point very shortly. Not very shortly, but within, I don't know, 20 minutes. So and please, you can freely leave this room if you're getting very bored, okay, about this very, yeah, I don't like. Yeah. Yeah.
That's this extra D, so.
Yeah, so I want to hurry up because I have a lot of things to talk about today. Okay, so let me. Anyway, this is very bad. Okay, from field point of view. Okay, and more importantly than this, like this is too large, and the axion coupling to matter fields gauge sector, which you want to use for search for axion, is too feebly coupled now. So that's very bad. You don't have any hope to search for axion from the beginning.
These people also made a very strong statement that they claimed that you couldn't find any accident from string theory bigger than yeah, so it's a very strong statement.
That you couldn't find it?
Well,
it was experimentally?
Yeah, that this extra D action couldn't accommodate a lower FA or a higher mass.
If I recall, they put a lot of theoretical constraints in there, what they call reasonable consistency.
Yeah, exactly.
But the strong conclusion is coming from with some strong issues.
Yeah. But we'll
yeah. So okay, so then let's ask here, okay, from motivated by our huge desire to search for axion. Okay, so can axion decay constant in this line in the implicit axion window, okay, which is upper bounded by 10 to 12 GeV and lower bounded by 10 to 9 GeV. Is it possible to have such a low decay constant in extra-dimensional axion scenario? The argument of these people is that's not possible. Okay, but I'm going to today refute their arguments. Okay, so we ask here, because we have been only talking about the flat case, what about the warped case? Now, for the purpose of now embedding the extra-dimensional axion scenario in the warped 5D guts, okay, let me consider promoting the MSS engaged group again to the 5D gauge group that is propagating along the warped extra dimension, compact extra dimension. And also let me introduce the Berkeley U1 theory for the axion. And because in this talk, I'm not aiming to solve the hierarchy problem, okay? I'm gonna have the position of this IR brane as a free parameter. And let me consider for simplicity localizing this Higgs field on UV brane, as well as matter fields on UV brane. And also for breaking SU5 to MSS engaged group, let me introduce the Higgs field transforming as a 24 under SU5, whose value we're gonna break the SU5. But once I say this, maybe some of you maybe immediately want to ask me like, well, you're saying like you're talking about embedding extra-dimensional axion in the orbifold GUT, but it's not orbifold GUT because in orbifold GUT, like you don't use the value of Higgs to break the symmetry spontaneously. Instead, in orbifold GUT, what you do is to impose the different Z to parity eigenvalue to XY boson and the MSS integer gauge field. Okay, if you impose a different Z to parity, and then you don't need to introduce this to break SU5 into MSS significant gauge group. But because if you do that, because the UV brane localized operators does not respect SU5, you are going to have a slight spoiling of the gauge unification because of threshold effects. Therefore, let me focus on this simple scenario for nice gauge unification. And these gauge groups, the gauge fields propagate along this warped extra dimension. Okay, now let's talk about, again, the running of the gauge, how running of the gauge coupling can change now in this warped setup. Again, we go back to the 5D scalar QED for that purpose. We go through the same procedure that we did in flat case, which is to think about, introduce, we think about first the radiative correction photon self-energy. And for that purpose, let me introduce the some scalar, Burke scalar, charged under this U1 hypercharge, let's say. And to regularize this divergence that arises in photon self-energy radiative correction, let me introduce the regulator, PV field. If you work out the KK spectrum by looking at the y-dependent part of the equation motion, what you find is this, where the blue shows again the charge field, KK excitation, of the Burke scale of 5 whose Burke mass is 0. And the orange shows you the Higgs excitation, Higgs spectrum of the PV field. Now you can already see there's a huge difference between the warped case and flat case. Why? That's because for every single Higgs excitation of charged field, now you find there's corresponding Higgs excitation PV field whose mass is not comparable to the UV cuff, but whose mass is almost equal to each Higgs excitation of the charged field. Okay. Okay, again, by taking into account all of this guy's contribution to photon self-energy, now you find because of quasi-degeneracy between these excitation masses, now you see effectively this KK excitation contribution to photon self-energy basically vanishes.
Can I ask a extremely naive question? I haven't thought about this setup before. So on this picture, where is the UV scale?
UV scale is set by the Burke mass of the PV field,
Oh, it's
which
okay.
is capital M. Yes. The capital M is
So should I be surprised to find a bunch of modes from the regular field down in the physical range of energies instead of high up?
yeah, that's right. That's the key point
That's the
of
key
this.
here, I understand, but like, why is that consistent? Why is that? I mean, normally regulator is supposed to be some short distance thing. And the high energy thing.
Yeah.
And here it seems like the regulator masses, especially with your PV field.
Yeah.
At least from the picture of the same order as the physical excitation. Like the blue ones. So why is that okay?
Why is that okay?
Or is that even, is that a correct statement in the first place? Am I reading the picture correctly? Is that right? So are the physical excitations, do they have the same energies roughly as the regulator
Yeah.
excitations?
As far as Higgs excitations are concerned, yeah.
This is a property of the warp geometry. That puts a corner or redshifted down, and there's still a local cutoff, but
Okay, so this should be surprising. So
Yeah.
it's very different.
no, but the cutoff also shifts down, right? There'll also be the
The
cutoff.
cutoff of this
It's
Higgs excitation of PV field, they go to lower line than the flat case.
Oh.
And this is non-trivial observation made by the Alex tomorrow.
I see. So
And yeah.
you don't lose the usual UVIR decoupling here or anything like this. Something very special to work
Mhm.
with. Thank you very much. Okay.
And then because of this quasi-degeneracy, their contribution to photon self-energy just get cancelled by the PV field excitation. Okay, therefore, in the end, as a result of this, in the end, photon self-energy is almostly effectively contributed only by the zero mode, not excited mode. Okay, which is very different from the flat case, because in flat case, notice that all KK tower were still making contribution to photon self-energy, giving rise to power. But here that doesn't happen. Therefore, the point is the H0 mode correlator still logarithmically depends on UV cutoff because of this single PV field. Therefore, the point is running of the gauge coupling still remains a logarithmic power law. There is a case when the form momentum is still smaller than taking mass gap, because in this case, the only relevant degrees of freedom is zero mode, the gauge field, okay, 5D gauge field. Therefore, the appropriate observable for investigating running of the gauge coupling is the zero mode two-point correlator of the gauge field. But now, if the form momentum, if you want to think about the form momentum greater than taking mass gap, now you're entering into the 5D theory. So here, therefore, the appropriate observable for investigating running of the gauge coupling should change. It shouldn't be the zero mode correlator of the fold. But then the suggestion is, okay, we need to look at so-called front grain correlator. Okay, and here the GP ZZ prime is the 4D Fourier transform of the 5D gauge field correlator. Okay, so therefore, when you think about this 5D gauge correlator whose external line sitting at the UV plane, this is what I mean by here, front grain correlator. Okay. And when the form momentum is comparable to some energy scale, okay, in between two branes, or that is greater than this energy scale, if you look at the action, if you write down the two-point correlator at tree level, and then you will see that this gauge correlator, by the gauge correlator, becomes dominated by the higher dimensional terms, okay, which is quadratic in the field and which is suppressed by powers of this energy scale T. Okay, therefore, that means you have a breakdown of the EFT. So you cannot rely on the radiated correction of this correlator to investigate the running of the gauge coupling. But as far as the form momentum is still smaller than the isocurvature, okay, or Planck scale, you can still rely on this 4D Fourier transform of the gauge correlator, whose external line is sitting at the Planck brane. And that's because you're sure that this will be dominated by the kinetic time of the gauge field. So you can study, the point is radiative correction to this Planck brane correlator to study running of the gauge coupling. And now, if you compute the self-energy, the radiative correction to the Planck brane correlator, then you may wonder, you may consider this kind of diagram as a contribution to radiative correction, where you have a photon propagator coming from the Planck brane, and let's say you have a charge scalar, okay, and you have another brane to Burke correlator, okay, and this guy corresponds to the Planck brane, the Burke brane correlator. Okay, let's say external momentum here is given by P, momentum P. So, and let's say this position is Z and this position is Z prime. Okay, and then you have here K inverse for K inverse to Z. And you have another scalar propagator here, which is, and let's say the internal momentum is Q. So you have here, sorry, if this is Q and this is P plus Q. And you have the scalar propagator here, which is P plus Q. This is propagating from Z prime. And this is propagating from the Z prime to Z. So as Q and Z prime Z. You have another propagator here, propagator, which is P from Z prime to K inverse, okay? And for each vertex, you have 2Q plus P mu. And here you have, I don't know, like 2Q plus P mu, okay? And you make a product of these guys and you integrate over not only for momentum, also you need to do integral over ZZ prime, okay? The point is, if the form momentum, if you look at the form momentum, okay, which is greater than the Z inverse, giving you the energy scale relevant to this brane here, sitting here. When PZ is way greater than 1, what happens is this propagator, where is it? This one will reduce to the simple expression. Meaning that you have exponential suppression for this propagator. So that means effectively, those contributions corresponding to this kind of diagram will make a dominant contribution to this integral, okay? But the other guys will be suppressed. Therefore, what that tells you is radiative correction to this Planck brane correlator will be dominated by the region close to the UV brane. Okay. And most of the KK excitation we're gonna have a profile localized towards IR brane, whereas the zero mode, we're gonna have profile localized towards the UV brane. Therefore, effectively, the UV localized, effectively, this radiative correction to the Planck brane correlator will be mostly contributed by UV localized zero mode. So again, it's even if we enter the fiber theory, now we see that only zero mode makes effectively most of the contribution to the radiative correction to the Planck brane correlator. So that's the lesson that I want to tell you here, okay? In addition, it turns out in Warped case, there's another contribution to the running of the gauge coupling from the kinetic time itself of the gauge field, okay? And this is, you may call this a tree-level contribution to running of the gauge coupling, which sounds crazy, but that's true. That's because in Warped case is different from Blood case in the sense that the compactification radius is related to the energy, the hierarchy between the energies of these two branes, okay, which does not happen in the flat case. Therefore, there's a true level contribution to the running of the gauge coupling. So just forget about what I have told you now, okay, just forget. In sum, what I am telling you is for the effective gauge coupling running is contributed by just normal zero mode, which is just MSSM field, plus additional the kinetic the true level contribution, which I here parameterized by the CFT contribution. So this contribution appears above KK mass gap. Below KK mass gap, you don't have this contribution. You just have normal MSSM gauge coupling running. Okay. So therefore, because now you know the expression of the running of the gauge coupling in terms of the CFT, the contribution, CFT, the true level contribution, and also the zero mode contribution. Now you can try to see if you have a right gauge coupling unification. Okay, by varying this parameter and KK mass gap. For example, let's look at the purple and orange where you have a same CFT contribution. Okay, so this contribution is the same for purple and orange, but they differ from each other by having different KK mass gap. Okay, and purple has here the smaller KK mass gap than the orange one. But now you see that because purple has a smaller KK mass gap, it starts to deviate from the MSSM gauge coupling running at the lower scale than the orange. Okay. On the other hand, you still see that there's no any problem for the gauge coupling unification. Okay, so we have a right gauge unification in the 5D warped case, and we don't have a blow up of the gauge coupling beyond the KK mass gap. Okay, so it seems that we don't have to require the KK mass gap to be comparable or greater than the unification scale. Okay, to have a perturbative gauge unification. That's the point.
And I should say that this was well known. And of course, Gongjun just went through that quickly, but it was well known, but the Berkeley group should have known. It's like obvious that.
And yeah, and Ben Safudi and they were so confident. Yeah. And that gave us project good, very good. Yeah. Very good. Okay.
That's
Yeah.
nice, positive.
Okay, so I have told you gauge unification is done in 5D warped case. Okay. But what I haven't told you so far yet, what about the expression of the expression of the decay constant? Okay, when you embed extra-dimensional axion scenario to the 5D warped GUT. Okay, so let's go through with the let's go through the axion decay constant expression. Okay, for that purpose, let me get into details of extra-dimensional axion a little bit. Getting back to getting back to the question raised by the KIF. So what you need to do to have extra-dimensional axion is, again, you assume some Berkeley-Yuan gauge symmetry and you impose boundary condition to the C mu, R1 free KISS and S1 KISS C5, different boundary condition. And if you give boundary condition in a way that you have a zero mode of C5, whereas you don't have a zero mode of C mu, okay, and then in 4D, you're left with a C5 zero mode, okay, which will be identified with the axion. And if you perform under this U1 Berkeley gauge group, this Berkeley gauge field will transform with the gauge transformation parameter, importantly, which satisfies this condition. Okay. If the gauge parameter, when it winds around the compact dimension once, if it is still equal to its original value, then this is called small gauge transformation. Whereas if it's enhanced by integral multiple 2 pi, and that's called the large gauge transformation. Under small one, the Wilson loop is invariant. But interestingly, on the large one, you see that this angle shifts by integral multiple 2 pi. So therefore, that means really the phase of the S1 component of the Wilson line is really compact angular variable with periodicity 2 pi. That's why we can identify, we can think about identifying this with the axion. And now in this way, you see that how the U1 Borg gauge symmetry is translated to the theta gauge transformation, which is the 2 pi shift by the theta shift by 2 pi.
What's happening with all the other fifth components of all the other gauge fields?
There's still KK tower.
No, I don't mean the KK tower.
Oh.
This is the fifth component of the U1 gauge field.
Yes, that's right.
But
Yeah.
there's a fifth component of all the other in SU5.
They get eaten to make the massive KKs, that's all right. So that there'll be a massive SU5 and it eats the.
And for MSSN gauge group, we impose the opposite boundary condition to the Burke gauge group of the MSSN. So that there it's opposite. The CMU has
You have the 24, but
Okay,
yeah, you have the 20, but that's on the boundary. I think you put it on the boundary.
Yeah.
Let's say you look at an SU5 gauge boson in the bulk. Okay, when you compute the KK tower, the A5 components are the longitudinal components of the massive KK. So they just get eaten in the usual way. But what you do for the axiom is you do the opposite, as Gongjun Choi said, is you project out the gauge field and keep the C5, and that's your axiom. And then it has all these nice properties of that was well known, right? People knew this starting back.
we thought it was well known, but yeah, it seems like
and these were coupled to GG dual.
Yeah, exactly.
yeah, that's
I
right.
guess you'll mention.
Yeah, I'll get that. I'll get that point. Yeah, I will
This
get.
is well known in string theory, is what I meant. Some of this stuff, right? With the
Yeah, probably.
Wilson line.
Yeah, absolutely. Yes. Okay. Now, given how we can get the axion from zero model of the fifth component of the Burke gauge field. Now, let's work out the decay constant. Okay. For that purpose, you need to solve the equation motion of the C5. Try to figure out what C5's y dependence. It's flat actually. Okay. And also, you need to canonically normalize kinetic tone on this. In that way, you can get expression of decay constant. And in sum, it turns out that decay constant is given by, again, of some vector, KK mass get. Here, the MIR is just a KK mass get divided by pi. So again, this is up to order 1 factor. This is equal to KK mass get. So same as the flat case. Now, probably just get back to this is a point that Keith was wondering. Now, in the action, now what controls the axion coupling to other thing is, of course, that's the U1 gauge symmetry in the Burke. Okay. And because of this U1 gauge symmetry, you can have this gauge field in the kinetic term, or it's Simon coupling to other gauge structure. This is gauge invariant up to boundary term. Or CM, this gauge field can appear in the covariant derivative of some charged field. These are the only possibility for appearance of a CM in the 5D action. And that's because the gauge invariance requires the gauge redundancy under the U1C. Now at the moment, let's forget about these other couplings of CM, but let's only consider the case where you only have a kinetic term for the Burke gauge field. But then in classical mechanics, we know that when you have a free particle described by this Lagrangian density, where x is generalized coordinates, its conjugate momentum generate the symmetry that asks x to shift. Okay. Another way to say this is that the P here is conjugate momentum of generalized coordinate serve as kind of playing a role of the current generating this shift symmetry. Okay. Therefore, you can view the equation of motion of this generalized coordinates as a divergence of the current. If you apply this to this field theory, viewing the dynamical gauge field as the generalized coordinate, and then you see that the conjugate momentum of this Burke field, which is given by this, which is 2 form, carrying 2 indices, this should generate some symmetry that shifts this gauge field. Okay, and because this current is carrying 2 indices, this symmetry is one-form symmetry. And we call the symmetry one-form electric symmetry. Now, you can decompose this one-form symmetry into R13 piece and S1 piece, and especially under this S1 piece. Now you can observe that under this electric symmetry, the theta angle shifted by this parameter, which is line integral of this parameter, okay, which ranges from 0 to 2 pi, which lies at some value between 0 and 2 pi. And this is nothing but, from Bordy point of view, this is nothing but the axion shift symmetry, okay? So therefore, what you see here is the 4D axion shift symmetry is actually originated from electric symmetry of this gauge theory, or gauge theory, okay, not the gauge symmetry itself. What does that tell you? What lesson can you take from here? I told you axion shift symmetry is originated from the electric symmetry, and if you break axion shift symmetry, that tells you how you can actually generate axion potential. Therefore, the axion potential generation mechanism must be directly related to the breaking of the electric symmetry. Okay, therefore, anything that can make contribution to the right hand side of this equation of motion of Cm will directly tied to the axion potential generation mechanism. Now let's get back to the 5D action that we have, where the Cm now also coupled to the other gauge sector, or QCBH sector in the action. But then because you have a Cm here, okay, you know that this term will appear in the equation of motion, which is conservation equation of two-form currents. And therefore, that gives you this equation, divergence of the two-form currents, whose dimensional reduction gives you familiar ABG normal in 4D. Okay, so and this is the very familiar way of generating axion potential. Okay, by coupling axion to the gauge sector. Okay, so indeed we see that the breaking of one-form symmetry really gives you the mechanism for generating axion potential. But this is not the only way to source divergence of two-form currents. You can also introduce, as I said before, you can also introduce charged field under this U1C. Okay, and that's because if you do that, and then in the covariant derivative, you will have a Cm. Therefore, you know that will make a contribution to the right-hand side of the equation of motion. Okay, breaking the conservation of the two-form currents. So this has to be, therefore, because this breaks the one-form symmetry, this has to be directly related to the mechanism that lifts up the flat axion direction, axion potential. This is just symmetry perspective that's denied. The theories always tell us, but to check this really happens, you really have to go through this, how this axion potential gets generated, okay, by working out really the case by case, working out how axion potential generation happens. Okay, for that purpose, first let me consider introduction of the Burke charged field and the other charged field localized on UV and IR plane. Okay, which transform in this way. But then the key point here is you can only, if you do that, you can always write down the gauge invariant 5D action, okay, Burke action and brain localized action. And if you integrate out the Burke field, and then you will find this indeed gives you the theta dependent term in the action for the action, which is interpreted to be the axion potential, okay? And getting back to Keith's question, this is problematic misaligned contribution to axion potential. But normally in this kind of theory, the Burke mass, so nu k is basically Burke mass of the charge field. And that's way larger than the inverse of compactification radius. And given that, now you have the exponential suppression of the true level operators induced the additional misaligned contribution to axion potential. So because of this exponential suppression, the extra-dimensional axion can have exceptional quality, okay, compared to the 4D field-threaded axions. But now you may wonder, well, like this seems to be arbitrary setup because I introduced not only Burke charged field, which has to be there to study the one-form symmetry breaking, but also I introduced a localized field. So what if I only introduce a Burke field? Okay. Okay, let's do that. So there's no localized charged field. There's only Burke charged field. But if you do that, then there's still on the board already the correction to the axion potential. And let me denote the Burke field by psi here then, now, this time. And when this charge field wind around the compact extra dimension, because this is gauge theory, this wave function of psi should obtain something like e to the I theta, okay, because this is gauge theory, and which is nothing but the Harmon-performed phase. So that means, again, if psi winds around the compact dimension ones to obtain this argument, And then its wave function should be modified by this Haber-form phase. And this will tell you now the theta-dependent decay spectrum of this charged field. And now you can go through a computation for this charged field, KK tower's contribution to the vacuum energy by summing all those log of the functional determinant of this charged field, KK citation. You can do that. And if you think about what is the summation of all these log factor, it's basically log of some function whose zero coincide with the KK masses. Okay, so that means you can just use this relation as a spectral function to compute this theta-dependent vacuum energy. Okay. If you do that, which was done by Hosotani long time ago, which was also here, I don't know, some of you may already met Hosotani many times here. If you do that, and then you will get this kind of correction to the potential, axion potential, which is again bound by exponential suppression. Okay, and also which is proportional to the KK mass gap to the fourth power. In flat case, you will have the same result, okay, proportional to KK mass gap. But extra-dimensional axion in warped case is more advantageous because the KK mass gap is low line in the warped case than the flat case, okay? So extra-dimensional axion in warped case is, I think, has better quality, even better quality than the flat case. Okay, now given our knowledge of the running gauge couplings expression parameterized by the CFT the tree-level contribution, and also the KK mass gap, and also given the expression of the decay constant, okay, now you can try to see whether you can have the perturbative gauge unification, okay, still having the decay constant as low as 10 to 9 GeV. If you do that, you will realize you can achieve both of the purpose, okay? For example, if you look at the purple and green here corresponding to a decay constant to 9 GeV, 12 GeV, you see indeed you can have a perturbative gauge unification. As far as you have mild hierarchy between the ADS curvature scale and universal compactification radius. So warp factor is larger than usual case, Randall-Saunders model, where you try to address a hierarchy problem. But you can achieve these two goals simultaneously if you have the slightly greater warp factor than the Randall-Saunders model. Now, okay, so these two proposals are achieved successfully, but then you may remember one of the very slides that I showed you at the beginning. Okay, when I talk about the quality problem, and I have told you the two possible UV origin of the source of the quality problem. One was the higher dimensional operator. The operator one was the small instanton effects. Okay. And because even if I have told you about the perturbative gauge unification, in principle, because this alpha can be as large as 1, okay, saturating the criteria for the applying the perturbation theory, you may wonder, what if I have a case where gauge unification happens, okay, happens in a way that alpha gut is as large as 1. But then the case, if you compare the instanton factor, okay, to the case where you have a usual gauge unification with alpha amounting to 1/24, then you see a huge enhancement in the exponentiated instanton action. So therefore, this makes you worried about whether we have a huge small instanton effects induced misaligned contribution to axion potential. 10 to the 62. The enhancement by this factor is really big. So that makes you really worried about situation, worried about the misaligned contribution to axion potential. Okay, and furthermore, not only that, I am talking about MSSM, right? And in MSSM, we know there's an avoidable gauge invariant operator QQQL, where Q and L, these are SU2 doublet. And this always happen in MSSM Lagrangian. This is sitting there, just sitting there. That's because you have always the Higgs triplet, okay, which when get integrated out, which always produces this kind of operator, four fermion gauge invariant operator. And if you use this four-Feynman operator for closing Feynman zero mode image from small instanton, it's very, very bad because it makes this instanton integral over size of instanton more UV dominated by giving more negative power to rho. So presence of this operator makes UV instanton contribution bigger than the case without this kind of operator. And this bad situation is happening, is unavoidable in MSSM. So now this makes you really
Back to my earlier question. So if the coupling is real, I'll be totally fine, right?
if coupling is real, they're totally fine. That's right.
Because the
Yeah, that's right.
QCD phase, additional phase.
Just have a
is the same as
that's right. Just have a heavy axion. That's right. You're right.
That's what we want.
Oh, heavy axion. Okay. If you want heavy axion, yes, that's what probably yes. Okay. Now, given this fear for the huge contribution to axion potential, okay, let's actually go through the computation for SU2 instanton-induced axion potential correction. Okay. I'm looking at SU2. That's because I have this Latin operator here, which is only transforming under SU2, not SU3. So this is a dangerous diagram. Okay, that may give you the huge delta V theta. Okay, from SU2 instanton, now you know there are 9 quark zero mode, 3 flavor, 3 color, and also you have a 3 lepton zero mode. Okay, 3 flavor, and also in MSSM you have 4 gauge nodes. Okay, and you have 2 Higgs nodes. So by taking out and by closing Fermion zero mode of these guys, for example, and here by proper mass insertion or higher dimensional operator insertion, okay, you can go through the computation. And for closing Higgs zero mode, let me just use the mass insertion. Okay, where mass is given by soft mass of lower gravitational mass, and I take it to be 100 TeV here for simplicity. But you can have higher gravitational mass, making situation more in dangerous, putting situation in more dangerous situation. But let me just take this gravitational mass here at the moment. If you estimate this, very bad. You will get the huge misalignment. Okay, it's way larger than 1. Okay, the delta V is even greater than V theta. So it's very bad. Okay, very disappointing. But this is not the end of the story. If you know what happens in the 4D dual theory, okay, where the gauge field, okay, whose running we study here, if you remember that gauge field coupled to CFT sector as well weakly, gauging the weakly gauging the global symmetry of the CFT, you know that there must be also CFT contribution to the running of the gauge coupling, so that there must be also the zero mode of the fermions charged not only under SU2 but also the